So this falls as the second unit in the Alberta program of studies right after kinematics, where you actually learn about Newton's laws, his laws of motion. So it's going to kind of tie between Max's presentation. And we're going to kind of use the laws of motion to help describe Newton's law of universal gravitation. So, big ideas that we want to get from this lecture. We want to learn what the universal law of gravitation is. We want to learn what the constant is. We want to kind of talk about the relationship between mass, force, and radius. Much of this can be described by his equation that he created, but we're going to go into more detail about that as we move on. We're going to provide some real-world examples of how the law of gravitation, how we see it in everyday life, and how we've used it to actually discover different parts of the universe and whatnot. And then we're going to relate it all to the three laws of motion, as I mentioned. So those are some of the big ideas. So as a recap, these are the three laws of motion. So the law of inertia, as we talked about earlier, that is when an object is at rest, it will want to stay at rest, or if an object is moving at a constant velocity, it's going to want to stay at that constant velocity unless acted upon by an unbalanced force. So essentially, if you have mass, you have some sort of inertia. The more mass that you have, the more you're going to want to stay in that constant motion, the harder it is to move you. The second one is force is proportional to mass and acceleration. And then the third law is that every action has an equal and opposite reaction. So if I push down on the table is pushing directly as hard back on my hand. So, food for thought. So here's a question. We've got these two water bottles right here, right? This one's filled to the top with water. This one has just a little bit of water. I think it's safe to say that this water bottle will weigh more. I think that's pretty obvious. So the age-old experiment, if I'm to drop these two water bottles from the same height, are they going to land at the same time? Is the one with more mass going to land at the same before the lighter bottle, or is the lighter bottle going to drop and land before this one? Do you have any thoughts about which one we think is going to land first?
The heavier one will land first because it has more. I think the heavier one will land first because it has more mass.
Okay.
So mass is, yeah, that's what I think.
So now this is where a big confusion can come in. Which one's going to hit the ground with more force compared to which one's going to hit the ground first? So which one do we think is going to hit the ground first?
Heavier one.
Okay, and which one do we think is going to hit the ground with more force? Heavier one. So can you just turn? Turn. I'm just going to quickly drop these two from the same height, and let's see what happens. And so it might have been hard for you guys to see there. Oh, back over here. But they actually land at the same time. So something that we're going to learn is that the acceleration of an object, no matter what how heavy it is, all objects fall at the same rate. Okay, but yes, the heavier one does hit the ground first. Sorry, ignore that. The heavier one does hit the ground with more force, as we've kind of predicted. Second question, does the moon pull on the Earth with gravitational forces? What do we think? Does the moon pull on the Earth?
Yes.
Yes, I would say so too. How much compared to that of the Earth pulling on the moon? Do you think it's less? Do we think it's more?
Way less.
Way less. Okay. And then why does the moon orbit around the Earth? So we're not going to answer that because that's a big question, but we'll talk about these as our lecture goes on. So our objects were falling at this magical number, 9.8 meters per second squared. That's the acceleration due to gravity on the surface of Earth. This was initially proposed by Galileo about 400 years ago, and it was later proven mathematically by some of Newton's formulas. So what about in space? What keeps celestial bodies in orbit? So I found this little interactive here that I'm going to pull up, and it's talking about the relationship between force, mass, and distance between objects. Come on, click. Okay, perfect. So these arrows represent their vector of force. So they're telling you what direction that the force is going in, okay? So what is something that you noticed right away about these vectors? Anyone tell me?
Are they equal?
Yes,
Yeah, they look the same.
they look the same. And they're both pointing towards one another, right? It doesn't matter where I move this, they're always going to point towards each other. But what happens when I move them further apart? What happens to the forces?
Get smaller.
They get smaller. What happens? So then we can determine that as we move two objects farther apart, the gravitational pull decreases. It's inversely proportional. So what about if I increase the mass? What do we notice? We're increasing the mass of the planets. What do we notice?
Force increases.
Force increases. So we could say that the force is actually directly proportional to the mass of the objects. So I'll exit out of that and head back to our PowerPoint. So what you can kind of see through that visual representation is that it's all about proportionality. So the force is directly proportionate to the mass, the two masses. So as they increase, the force will also increase. And it's inversely proportional to the square of the radius. So as the radius, so the distance between the two objects, as that increases, the force is going to go down, right? So this was the big relationship that Newton found. This is, in essence, the law of gravitation. This is his big finding. It wasn't until years later where we discovered the gravitational constant, and this was actually determined by a different guy through experiments, Henry Cavendish, about 100 years after he determined that proportionality formula. But I want to look at a couple of examples here, and if I could get you, Max, to move over to the board. So, when considering our formula, so what do we think will happen if we say we're to double this mass, 2m? What do you think would happen overall to the force?
Increase.
Increase, yes. Can we say by how much, necessarily? If we were to say plug it into our formula, proportional to 2m times m over r squared. Well, you can just take the constant out, so your force would increase by a factor of 2. What about if we also increase this one by a factor of 3? So now we have 3m and 2m. How much do you think the force would increase?
6.
6 times, right? So you can imagine if this is a 3, you bring those out, 2 times 3 and 1 over r squared, right? And this is 6 total. And so what about, I'll erase the 2 and I'll erase the 3, because we want to stick to simple mathematics here. What if we increase this, the distance, by 2? This is where it can be a bit tricky. How much would our force increase or decrease? First off, would it increase or decrease if we spread them out further apart? Would the force increase or decrease?
Decrease.
It would decrease, yes. So by how much? If we were to plug in a 2r here instead, well, of course, by mathematics, you have to square both numbers inside. Your new formula becomes m1, m2 over 4 r squared. Taking out the constant, and you end up with force, it's 1/4 m1, m2 over r squared. So your force would actually decrease by a quarter. Does that kind of idea the relationship between mass, distance between, and how they're proportionate to force, does that sort of make sense to everyone? Cool. I'm going to keep on moving. So, including the gravitational constant that Cavendish came up with, they were able to create Newton's law of universal gravitation, which is this beautiful formula. So this is able to, you can find the force between any two objects in the entire universe, simply based on their mass, both their masses and the distance between the two of them. Okay, so back to our first question regarding the water bubbles. Why are these falling at the exact same rate? Well, we can actually use our equations to mathematically prove this. So let's say we're on the surface of Earth, which we are. Newton's second law, force is equal to mass times acceleration. So that it applies no different. If there's an acceleration due to gravity and there's a mass, then there's going to be a force, right? F equals ma. So let's say our object, being our water bottle, is on the surface of Earth. Based on Newton's universal law of gravitation, our object is a certain distance away from the center of Earth, right? So that means if we take the gravitational constant, the mass of Earth, the mass of the water bottle, and then the distance between the two, we can solve for the force. Because essentially what we have is this equals a force and this equals a force. Those are Newton's two equations. So if we actually cancel out, we have a mass of the water bottle on either side, and we end up with this formula. Now, gravitational constant, it's a constant, right? It's not going to change. Mass of Earth, it's, well, for our purposes, it's also constant. And the radius of Earth, also constant. So this number here, acceleration, is not going to change. So can anyone guess what number that would end up being? If we were to plug all these numbers into our formula. What number do we think our acceleration, what it would come out to?
9.81.
9.81, exactly. So using all these big numbers, but plugging into the formula gives you 9.81, which I find to be very cool. So what about the forces between the moon and the Earth? That was our second question. It sounded like we said that the force that the moon puts on the Earth would be less than the force that the Earth puts on the moon. However, you got to remember Newton's third law that we talked about, that every action has an equal and opposite reaction. Based on our equation here, we can interchange the mass of the moon and the mass of the Earth. It won't matter. It's only going to give us one force, and that force is the force between those two objects. So while one might be much smaller than the other, they're applying the exact same force on one another. So the moon is actually pulling on the Earth just as hard as the Earth is pulling on the moon. So then, back to that third question, why is the moon orbiting the Earth? You know, why is it moving? And why is the Earth not rotating around the moon, right? If they're pulling on each other with the same force, why is only one moving? Well, think about it this way. Imagine you have your car, you put in your car in neutral, it's on flat ground, and then you have this little car beside. Which car is going to be harder to push? This one or this one? The bigger one, of course, right? It's not, I mean, it does weigh more, obviously, than this little toy car, but it's not like we're lifting the car up, right? We're not defying gravity, because gravity is towards the center of the Earth. We're not going against gravity, but it's all related back to Newton's first law, inertia. The more mass something has, the more inertia it has, so the more resistance it has to motion. So if I'm pushing this car, it's going to be harder to push than this light dinky car. So if the Earth with a big mass and the moon with a smaller mass are pulling on each other, the moon has less inertia than the Earth, right? So the moon is going to be more susceptible to that force, and it's the one that's going to be moving. And then, of course, Earth is orbiting around the sun with a velocity as well. And for the same exact reason, right? Because the sun has more mass than the Earth. So that is all completely related to inertia. So relating this to what science, technology, and society. So we put satellites, there's thousands of satellites above us, right? So we end up putting our satellites into orbit, and they're moving at tens of thousands of kilometers an hour at a horizontal rate. They're actually caught in a perpetual fall because gravity is pulling them towards the center of it. But they have enough horizontal velocity that they're finding themselves in a perpetual fall. So they're constantly falling towards Earth, but they're also constantly moving sideways. They're basically falling and missing Earth. Does that kind of make sense as a perpetual fall? Same idea can go between the moon and our tides, right? So the moon has more inertia than the water on Earth, not the Earth as a whole, but just as the water. So they're pulling on each other with the same equal force, but since the water has less inertia, it's going to be the one that is moving towards the moon. And that's why we see our tides. Cool. So to end off, we're just going to check our understanding. So do we have kind of an understanding on the relationship between mass, radius, and force? All these proportionality equations. Is that thumbs up? Got a thumbs up from anyone? Perfect. Secondly, do we understand how to find the acceleration due to gravity on Earth's surface? So that was relating those two formulas to one another. Thumbs up, thumbs down. Two big thumbs up. And then do we understand why the moon is more affected by the Earth's gravitational pull and not the other way around regarding inertia? Cool. This is just a recap, but I think we kind of just talked about that. And so that is all for me, I think. Thank you.